Okay, so in this lecture, I'm going to go over the solutions to exam 2. Make sure you carefully work through them while I'm working through them, and bring any questions you have on about the exam on Friday. All right. All right. So let's see what do we got. So hopefully number one is pretty straightforward at this point. I did, by the way, grade. I did grade all the exams. So is this actually picking up my voice? Yes, it looks like it. All right. Um, I did grade all the exams. And I think for the most part, people got this first one right. Let's see. So number one, A. So we have f of x is equal to x to the sixth plus 2x squared minus x to the 4/3 um, plus e to the cosine x. So I'm going to first just write this term as x to some power. Oops. And then I'll take the derivative. So it's going to be 2x to the negative 2 minus x to the 4/3 plus e to the cosine x. All right. So now at this point, I can take the derivative pretty easily. So power rule on the first three terms. So this will give you 6x to the fifth minus 4x to the negative third. You reduce the power by one. Some people added one to the power. That's not the right. That's not right. Then you get 4/3 x to the 1/3. Oops. And then at this point, you need chain rules, e to the cosine x. So you take the derivative of the outside function, it's just e to the x function. So that's just e to the x. And then you multiply by the derivative of the inside function, which is cosine x. So that'd be negative sine x. All right. So that's that. All right, now number part B. So this one is going to require product rule and chain rule. So I'll write out the steps individually. So sine 3x to the fourth e to the x squared. So product rule says you take the derivative of the first function. So I won't just take the derivative yet. I'll just do the product rule times the second function. So it's just the derivative of the first function plus the first function times the derivative of the second function. Right now we can apply the chain rule. Again, as always, it's not necessary that you break it up in this way. Especially if you're taking an exam, you might be pressed for you got to think about time. But if you can do it, it doesn't hurt to separate it out this way. So now the derivative of this first term, this first thing right here. So I have sine of 3x to the fourth. So I take the derivative of the outside function, which is sine, so that becomes cosine 3x to the fourth times derivative of the inside function. That will be, I guess you could just write it as 12x to the third times e to the x squared plus sine of 3x to the fourth. Now we'll do this derivative here. So derivative of e, sorry, our outside function is e to the x, so the derivative of that is just e to the x, and then evaluated the inside function x squared times the derivative of the inside function, which is 2x. So that's all I'm looking for. You don't have to write it any differently than that. You don't need to simplify or anything like that. All right, now let's look at C. All right, so C is the function. So it's ln of e to the x plus x times 2x plus 3 sine of e to the x. Now the derivative, so all right, so I guess I'll break it up as you usually do. So we have to use product rule first of all. We have this product right here. So product rule says you take the derivative of the first function times the second function. And then I'm gonna have to go on to the next line, but now we're gonna add in this part right here. It's gonna be plus the first function times the derivative of the second function. All right, so now when we do that, so we'll take this derivative first. Remember, derivative of, so derivative of ln of x is 1 over x. In this case, we don't have just x, but we have ln of e to the x plus x. So something that some people I should point this out since I'm remembering. Some people said this. They did this first. Or some variation of it. And that's not true. You can't split the natural log up in that way. And then, of course, at this point, they canceled the ln and the e to get just x. But again, that's not right. You can't split it off in that way. So it's ln of e to the x plus x. It all goes together. You can't separate it. If it were ln of e to the x times x, then you could split it as addition, but we're not multiplying it here in this case. So I just want to point that out because some people did do that, or some variation of that. All right, so this first derivative that I underlined is going to be, so it's when you differentiate ln of something, it's the derivative of something over the something. So it's going to be e to the x plus 1 over e to the x plus x. And that's, of course, times 2x plus 3 sine of e to the x. And now we're going to add to that this other piece. So ln of e to the x plus x. I'm going to take this derivative right here. So the 2x becomes just 2. And then the 3x, 3 sine e to the x. Well, first of all, we have this 3 here. And that's going to be cosine of e to the x times e to the x. So it's this thing plus this thing. That's the answer. All right. With that, that's problem 1. All right, so problem 2. So for this, we have following equation: x to the 5th y plus x cosine y minus e to the y plus 1 equals 1, and we want to implicitly differentiate it, and then find the equation of a particular tangent line. So differentiating this first. So some people just forgot to do a product rule. So again, y is some function of x. It's changing with respect to x. So some people, when they differentiated this, they just differentiated the x to the fifth and y individually. They didn't use the product rule. Same here, and some people didn't even use chain rule at this point, or chain rule here even. So you got to make sure you use some product rule and chain rule. So when you differentiate this, you differentiate this. So you have to we're gonna differentiate each term. So you have to do this. For the first term, you have to use the product rule. So it's gonna be derivative of the first function times the second function plus the second function times the derivative of the first. Sorry, it's plus the first function times the derivative of the second function. All right, so that's the first term. So now we have this. So again, product rule first and then chain rule, because it's not just x times y, it's x times cosine of y. So this is a composition of functions. So chain rule. So when we differentiate this right here, we're going to get derivative of the first function, it's just 1. Derivative of x is just x plus x times the derivative of this second function. So cosine becomes negative sine y, and then times the derivative of the inside function, which is y, so it's y prime. Minus, so this one, no product rule, but we still have to use chain rule because it's not just y, it's e to the y, it's composition of functions. So this is just going to be e to the y plus 1 times y prime, and that's going to be equal to 0 because the derivative of the right-hand side is 0. All right, so we have a y prime. Now what we want to do is we want to solve for y prime. So we have a y prime here, and then we have a y prime here and y prime here. So we want to put those terms together and then throw everything else on the other side. All right, um, so we're gonna have x to the fifth, y prime, um, plus or minus, I should say, minus x, I guess y prime sine of y minus y prime e to the y plus 1. That's going to be equal to, let's see, this term doesn't have a y prime and this doesn't either, so those ones go on the other side. So negative 5x to the fourth y, sorry, minus cosine y. All right, so now at this point I can factor out my y prime. So I'm going to eat x to the fifth minus x sine of y minus e to the y plus 1 is equal to the right-hand side. And now I'm going to divide by this on both sides. So what we're going to get is y prime is equal to this. I hope you guys can hear me. I'm trying to talk as loud as I can. All right, so this is what you should end up with. That's part A. For part B, now we want to find the tangent line. Uh, so we want tangent line at the point x plus 1, 0. So this is point xy. So all right. So what we need to do is we have a point, but we need a slope. And remember, the derivative gives you the slope. So we're gonna plug this point in here. I guess you could say, I guess some people did actually write this, and this is actually the right thing to do. I haven't been doing it, but it didn't occur to me to actually do it. So you just like functional notation. So y prime of e plus 1, 0. So it's like we're evaluating y prime at this point. All right, so we get -5 e plus 1 to the fourth times 0 minus cosine of 0 over e plus 1, oops, e plus 1 to the fifth minus e plus 1 sine of 0 minus e of 0 plus 1. All right, so this should end up, cosine of 0 is 1, so you get -1. And then you get e plus 1 to the fifth, oops, minus e to the 1, and I guess you can switch things around and get rid of the negative. So it'd be e minus e plus 1 to the fifth. So this is the slope. So then the tangent line is e minus the y, or sorry, it's y minus the y coordinate, which is 0, is equal to the slope, which we just determined. So this right here, times x minus the x coordinate. So e plus 1. And that's it. You don't have to, you can just leave it like that. All right. Let's do number 3 now. All right, so we got this function, y is equal to cosine squared x times x squared plus 1 to the fifth divided by sine of x times x plus 1 to the 10th. And so this one you need, I mean, technically you can do product or change, or technically you don't need logarithmic differentiation, but it's gonna be horrible without it. And that's why I say suggest using logarithmic differentiation. So some people had trouble with this one too. So first step in logarithmic differentiation is to take the natural log of both sides. Like so. Oops. And now we're going to use our various log rules. So it's natural log. So I'm going to split this. So the quotient becomes a difference. And then the products become addition. All right, so that's that. All right, so now this becomes natural log of I'm also gonna, so we have cosine squared, so it's cosine to the second power, we have this fifth power, 10th power, so I'm gonna actually write those as oops, coefficients. So it's gonna be 2 times the natural log of cosine x plus natural log of, 5 times the natural log of x squared plus 1 minus the natural log of sine x, and then minus 10 natural log of x plus 1. Now differentiate. At this point, we differentiate. Oops. So differentiating, so we're using implicit differentiation on the left-hand side. So when you differentiate the left-hand side, you get y prime You get y prime over y. And now when you differentiate this, you get, so first of all, you get 2. And then you get negative sine x over cosine x. That's the first term. This term right here, 5. Oops, 5 times 2x or x squared plus 1. Now this term right here is going to be cosine x over sine x. And this term right here is just going to be, well, the derivative of x plus 1 is 1. So, and then you can just multiply the 10. So you get 10 over x plus 1. Then you multiply both sides by y. Well, remember, y is this right here. So let me just actually copy this right here. So yeah, you multiply both sides by y. It's not what I said. Let's go down here. All right. So it's just going to be y times the rest of the stuff. So it's going to be negative. You could write this as tangent x plus 10x over x squared plus 1 minus cotangent x minus that. You don't have to do tangent or cotangent. It's not necessary, but if you want. All right. This next one, sort of a trick question, just to make sure you're paying attention. So we have this, it says the length of a rectangle is increasing at a certain rate and its width is increasing also. What's the rectangle's perimeter? At what rate is the rectangle's perimeter changing when the length is 8 meters and the width is 5 meters? And it turns out that you don't need to know that stuff. Anyway, you'll see why. All right. Let's see. Can I? So we got this rectangle. So we have like this size increasing at. So we'll call this x and this is y. So this side's increasing, and it's at a positive rate. So let's see that this would be our width, I guess. So this would be 5, and then this is the height is increasing, or the length, I guess. I don't know. Whatever, it doesn't matter a whole lot. dy dt is equal to 2. This is meters per second. Meters per second. All right. So now the perimeter is just the sum of the sides. So there's going to be an x x, y, y, so it's gonna be 2x plus 2y. And we want to find how this is changing with respect to time. So we need this time derivative right here. So I just differentiate both sides, and you can see that x and y don't show up anymore. It's just dx t and dy dt show up. They're derivatives. So that's why that wasn't strictly necessary. So just making sure that you paid attention, that's all. And now we can plug in dx dt. That is 5, so 2 times 5 meters per second plus 2 times 2 meters per second. So it's 10, 4, so it's 14 meters per second. That's it. All right. All right, let's see, number 5. All right, so we got this parabola. I don't know if this can do parabolas. It doesn't look like it. All right. Try my best. So you got this parabola. Oof, this would be awful. Uh, I can't do it. That's a good thought. What if I do it on, no, the ellipse? If I do an ellipse, can I erase some of that? What if it does it erase the whole object if I do that? Yeah, fuck it, erases. All right. Whatever. I can't do it. Uh, it's as good as it's gonna get. All right, so you got this parabola y is equal to 3 minus x squared, and there's a box inscribed. Christ, that's terrible. All right, and so the vertex of this is gonna be a point on there. So that's how I label it in the picture, at least. And so we want to find the x that maximizes the area. This inscribed triangle, so rectangle, sorry. So you can imagine like this point right here is like you can slide it along the parabola. Of course, so we're taking x to be uh, sorry, so x can be between uh 0 and all the way over to here. So x, and that's a point on the parabola. It's the intercept actually. So x is gonna be between 0 and square root of 3. All right, so now the area, so we have this is a rectangle, so we have height right here is y, and then this length right here is x, but this length by symmetry is also x. So the area is 2xy. But y, but we're dealing with a point on the parabola, so y satisfies this right here, or it's equal to it rather. So it's 6x. Is this right? Minus 2x to the third. All right, so we want to maximize the area, so we need to take the derivative. So we get 6 minus 6x squared. And then, so that's the derivative, and now we need to find critical points. Because remember, critical points are if you have a minimum or a maximum, they're going to occur at critical points. So that's where you go to look for minimums and maximums. So if you set the derivative equal to 0, you get 6x squared is equal to 6, and then you cancel things out, you get this, and then you take the square root, you get plus or minus 1. X has to be positive. We're taking x to be positive, so this implies that x equals 1. Now you do have to check. Um, remember when you're trying to maximize a function, trying to find the maximum value of a function or closed interval, you need to check the critical points and the endpoints in the interval. But if you plug in 0, you're gonna have if x is 0, say if x is 0, it's gonna be give you 0 area, and if x is square root of 3, it's also gonna give you 0 area. You can plug those into the area function and see that. So this corresponds to the maximum area. All right. So that's that. Let's see, we're almost done. Shit. Okay. All right. All right. Let's get back into this. Sorry, I had to pause the recording for a bit. All right, so now we're on hold on, let me just make sure this is right. It's recording it. Okay. All right, so we're on number 6 now. And for this one, we need to use L'Hopital's rule to evaluate this limit. So we're taking the limit as x goes to infinity of e to the x over 5x plus x e to the x. First of all, um, if you just let x go to infinity and you look at the numerator and denominator separately, you see that you get the indeterminate form of infinity over infinity. So L'Hopital's rule does apply, so you can use it, and you do that by differentiating the numerator and the denominator separately. So the derivative of numerator is e to the x, denominator is going to be 5 plus, so product rule on this part is going to be e to the x plus x e to the x. And again, you let x go to infinity, you get the indeterminate form infinity over infinity. E to the x goes to infinity as x goes to infinity, and then e to the x and x to the x go to infinity. And if you add 5 to that, that doesn't that gonna make a difference anyway. So everything goes to infinity. So we can apply L'Hopital's rule again. So now we differentiate it one more time. So we get e to the x. So this becomes 0. This becomes e to the x. And then we do product rule here, so get x plus x e to the x. At this point, we can actually evaluate the limits after we simplify a little bit. So we have e to the x in um, um, each term in the denominator and in the numerator, so we can cancel that out to get 1 plus 1 plus x. And then finally, you get 1 over 2 plus x, and this goes to 0. So that's the answer for that one. All right, so here, this next one, this one's kind of long, but we gotta do it anyways. All right, so all right, number 7. So for this one, yeah, it's important to go over a problem like this because it basically you literally have to like practice everything we've learned so far, and also a problem like this is going to show up in the final. It almost always does. It's the same format though. You're going to be given the function and the derivative, so you don't have to worry about taking derivatives, but just worry about interpreting what the derivatives tell you. So we have this function, and then its first derivative is negative 2x over x squared minus 1 squared. And it wouldn't hurt on your own time to just verify that that's actually the derivative as practice. So that's the first derivative, and the second derivative is 6x squared plus 2 over x squared minus 1 cubed. All right, so um, for the first part, we need to state the domain of f, and um, f is defined everywhere. Defined everywhere except where the denominator is 0. So it's not defined at these points, plus or minus 1. So we just need to take it's every real number except plus or minus 1. So that means the domain is, an interval notation. It's this. Yeah, so this is the set of this set right here is the set of all numbers that are not 1 or negative 1. So that's the domain. What about the y-intercept, x-intercept? All right, so if you plug in 0 to the function, you're gonna get 0. So this is 0, 0 is x-intercept. And if you set the function equal to 0, that's the same thing as saying x squared over x squared minus 1 is equal to 0. And of course that implies that the numerator is 0, so x squared is 0, but that's only the case when x is 0. So this same point, 0, 0 is also the y-intercept. So a lot of people said they would say um, there is a y-intercept but no x-intercept, or there is a x-intercept but no y-intercept. So that's not true. There is an x and a y-intercept, and it's the same point. All right, so that's that. Now asymptotes. So let's look at horizontal asymptotes first. Finding the horizontal asymptotes, you let x approach plus or minus infinity. It's not always the case that you can combine both these limits, but in this case you can. So you can just compute the limits, both limits simultaneously, as x goes to plus or minus infinity. So we're taking the limit as f of x, which is x squared over x squared minus 1, as x goes to plus or minus infinity. So for this, you're going to divide by x to the largest, its largest power. And when you do that, you get 1 in the numerator, and then the denominator is 1 minus 1 for x squared. And then this point, you can clearly see that as x goes to plus or minus infinity, this term right here goes to 0. So you get 1. So that's the horizontal asymptote. What about the vertical? So vertical asymptotes are going to be where the denominator is 0, so it's plus or minus 1. But it's going to be helpful to know, yeah, so when x approaches plus or minus 1, it's either going to go to plus or minus infinity. We don't know which one, so it'd be helpful to know which one it goes to, which infinity it goes to. So let's just remind ourselves that f of x is x squared over x squared minus 1. And let's compute left and right hand limits. I mean, I guess this isn't strictly necessary. You don't have to write all this down if you can already see it, and then you can accurately draw your graph, but it's probably better to just write these left and right hand limits out so you can get it all sorted out on paper instead of trying to keep it in your head. Yeah, so when, as I said, when x goes to -1, whether from the left or the right, it's going to either go to plus or minus infinity, but we want to know which infinity it's going to go to. So if you take a number that's to the left of -1, so like -2, and you plug it in here, well, first of all, the numerator is always positive. So the numerator is not going to affect the sign of anything. So really, whether the sign is going to be determined by the denominator. And if you plug in, say, for example, -2 into the denominator, you'll get 4 minus 1, so that's positive. So this is going to go to positive infinity. All right, what about when x goes to -1 for the right? So, for example, again, we don't even need to worry about the numerator, so don't worry about plugging anything in the numerator, just worry about the denominator. So, for example, you could take x to be -1/2. So in the denominator, you get -1/2 squared. So it's 1/4 minus 1. That's going to be negative. So it's going to go off to negative infinity. All right. So now what about 1 and 1 from the left or the right? So if you approach 1 from the right, so again, you can choose like +1/2. You'll see that you're still going to get negative infinity. And if you go from 1 from the right, yes, sorry. This limit right here is the 1 from the left. This limit right here is 1 from the right. This, so you could take 2, so you'll see that when you evaluate it at 2, the function, you get plus infinity. Fuck. All right. So that's part C that fully answers that. Now we have part D, critical points. Um, so critical points are where the derivative is 0 or doesn't exist. So if you um plug in, if you set the derivative, well, let's just write it out. Set the derivative equal to 0, you get negative 2x over x squared minus 1 squared is equal to 0, and that's going to imply x is 0. So that's one critical point. This is one critical point. But notice that it's the derivative is not defined at plus or minus 1. However, those are not going to be critical points because critical points have to be in the domain of the original function, the first function you start with. So this is the only critical point. All right, so now part E. For part E, so we want to know when is f increasing or decreasing, and then we want to determine whether this critical point is a minimum or maximum or possibly neither. Maybe it's neither. Um, so increasing f is increasing if and only if the first derivative is positive. Now look at the derivative. This is the derivative right here. The denominator is always positive. It's x squared minus 1 squared. So the overall sign is going to be determined by the numerator. So this is positive if and only if the numerator is positive. And then, of course, you can divide by -2 to get this. So what this tells you is that f is increasing. Oops. Increasing on the interval -infinity to 0. All right, so that's increasing. What about decreasing? F is decreasing on sorry, it's f is decreasing if and only if the derivative is negative. And I guess this is technically not necessary, you just take the complement of this interval. All right, anyways, but it doesn't hurt to write it out. And again, this is if and only if the numerator is negative. Because the numerator completely determines the sign. Divide by -2, you get that. So f decreasing on 0 to infinity. All right, so now the function goes from, think about point 0, that's our critical point. It goes from increasing to decreasing. So that means x equals 0 corresponds to local maximum. All right, so that's E or F. So this is about concavity. So you want to know when is the second derivative positive or negative. So let's recall what the second derivative is. It's 6x squared plus 2 over x squared minus 1 cubed. So notice the numerator, we're gonna have like the reverse situation. Um, the numerator is always positive. Um, and so if we want to determine the sign of f double prime, we need to look at the denominator. Why is that? So why is that? Well, first of all, if you take a number and you square it, it's always positive, right? And if you multiply by a positive number, it's still positive. These are if and only ifs, actually. And if you add two to a positive number, you're also positive. But actually, not only are you positive, but you're greater than two. So the numerator is always positive. In fact, it's always greater than two. It's strong. This is somewhat stronger than being positive. All right, so all right, so now to determine the sign, we just needed to of the derivative, second derivative. We just need to determine uh we need to look at the denominator, see where that's positive or negative. All right, so f double prime is positive if and only if the denominator is positive. You can take the cube root to get rid of everything. That's not a big deal. Like that. And then you write it like this. And now you take the square root, so you get absolute value is if x is greater than one. And of course, this course, well, yeah, so this means that f concave up. I always forget this myself. I think it's concave up. Let me see. Let's see. Pretty certain it's concave up. Yeah, so this means concave up. Your derivative is positive means you're concave up. So it's concave up on uh, for all x satisfying this. And that corresponds to the set negative infinity to negative one, union one to infinity. All right, now concave down. So yeah, so concave down is when the derivative is negative. And this derivative is negative if and only if the denominator is negative. Take the cube root and then add one to both sides. Take the square root. Yeah, absolute value of x is less than one. So this means that f is concave down on the interval. So this inequality corresponds to the interval negative one to one. All right. All right. So no in all right, so we have concavity changes at one and negative one. And this is an inflection point is where the concavity changes and it's in the domain of the function, but negative one and one are not in the domain of the function. So yeah, so it has no inflection points. And instead of trying to draw this graph, I'm going to use Wolfram alpha. So hopefully you can see this. So wolframalpha.com. I've mentioned this before, and highly suggest using this when you're doing mathematics homework. So what we're going to do is we're going to plot. Use this. I'm going to use this to plot the function because I know it's just going to come out horribly if I try to draw it by hand. And let's try to make sense of it based on all the parts that we did. Um, so let's see. Let's plot this. All right. So you can see actually. I can also plot. Let's see. I can plot. First of all, you can see that there's this um, horizontal asymptote right here. This is what we found. We found that one was a horizontal asymptote. So if you plot that, y is equal to 1. Uh, I don't know why it's cooling like that. Uh, all right. Anyways, let's see. Can I plot this? Vertical asymptote? Hmm. No, I guess not. It usually allows you to. Maybe I'm not doing something right. Anyways, I think it's pretty clear though that we have a horizontal asymptote at 1 and then vertical asymptote at -1 and -1. And if you remember, so if you approach 1 from the right, you go off to positive infinity. Approach 1 from the left, you go off to negative infinity, and that's exactly what we found. Approach -1 from the right, you go to negative infinity. Approach -1 from the left, you go to positive infinity. So that's exactly what we found. So yeah, I would start with drawing the vertical and the horizontal asymptotes. That will give you an idea of what the graph is going to look like. And then here we have our local maximum, and that's really all. Yeah, that's all you need. And of course, this local maximum is also the x and the y-intercept. So all these can be put together to get a reasonably accurate graph of the function. All right. Let's see. So almost done. All right. So now for number 8. All right. So we have that f of x is defined as this answer, indefinite integral, or x to the third. Uh, Plus 2x minus sine x plus 5 dx, subject to the condition that f of 0 is equal to -1. And uh, we want to find f. So what we need to do is evaluate this indefinite integral. That's gonna From there we're gonna pick up a constant of integration, and then we want to use this condition to determine that constant of integration. So some people didn't use this condition correctly. They plugged in -1 for x and set it equal to 0. That's backwards. You need to plug in 0 for x and set the whole thing equal to 1. So it'll be clear what I mean when I actually do it. So let's evaluate this. So we can just do the integrate each piece individually. So these two are going to require power rule. So it's going to be 4x to the 3 plus 1 over 3 plus 1 plus 2 x to the 1 plus 1 over 1 plus 1. And now the indefinite integral of negative sine x, that's going to be plus cosine x. And then 5 is going to be 5x. And of course, you have your constant. This is what we want to determine using this condition right here. So let's simplify a little. So 3 plus 1 and the 4 cancel. So you x to the fourth. 1 plus 1 plus, and the 2 cancel, so you get x squared plus cosine x plus 5x plus c. So our condition is that f of, or constraint, or whatever you want to call it, so f of 0 is equal to 1. So that means when I plug in 0 in each x, it's going to equal 1. So I have 0 to the fourth plus 0 squared plus cosine of 0 plus 5 times 0 plus c, that equals negative 1. As I said, some people had it backwards. They evaluated everything at 1, negative 1 instead equal to 0. That's not what this notation means. So this is 0, 0, 0, and the cosine of 0 is 1, and then plus c is equal to negative 1. So that implies that c is equal to negative 2. And that's it. And then sorry, hold on. Right. Let's see. All right, so that's 8. And now we just have number 9. So we have this definite integral, and we want to compute it using u substitution. God damn. All right. So for this, the u sub is going to be e to the x plus x squared. If you let u be equal to that, and then, God damn, hold on. All right, let's try that again. All right. So indefinite, we have this definite integral. We want to compute it using u sub. So we have u is equal to this. So then du is going to be e to the x, 2x dx. And when you do this substitution, you'll get the following. So I'm just writing the original integral first. So this part right here, this is our u. And then the numerator together with dx is our du. So what we'll have is 1 over u du. And this we know how to integrate. This is just going to be ln of u, absolute value of u, ln of absolute value of u, evaluated at 1 from 1 and 0. But now u, don't forget, is this right here. So we plug that back in. So we get e to the x plus x squared. Is that right? Evaluate from 0 to 1. And now we evaluate this expression at the endpoints. So e to the 1 plus 1 squared minus ln of e to the 0 plus 0 squared. So this is going to be e to the e plus 1. This is actually the value ln of, so this is 1 and 0 is a 1. And then ln of 1 is just 0. So we end up with this ln of e plus 1 without absolute value. Because e plus 1 is positive. You don't need absolute value. And that's it. All right.